Okay, so welcome to session 3 of DISC 2020. We will start with the winner of the Best Paper Award. This is the improved bounds for distributed load balancing. The authors are Sefer Sadi, Aaron Bernstein, and Zachary Langley, and Zachary is going to give the talk.
Okay, thank you. So thanks everyone for coming. So yeah, I'm Zach Langley, and this is the talk for the paper improved bounds for distributed load balancing. So let me just jump right into the problem statement. So in the load balancing problem, the input is a bipartite graph on clients and servers, and every client comes with some positive integral weight. And the goal is to compute some assignment, which is a map that takes each client to some adjacent server. And there are several objective functions you could consider here. Two natural ones. One of them is to minimize the maximum load of the largest server load, where the load of a server is just the sum of the weights of the clients assigned to it. And another is to minimize the sum of the squares of the server loads. And in fact, the algorithms that we develop here are approximately optimal for both of these objective functions at the same time. This problem, the min-max version, goes by another name. It's scheduling jobs on machines with restricted assignment, where you want to minimize the parallel completion time. Okay, so we consider this problem in the distributed models of the local and congest models. So the input graph is a communication network. The nodes communicate with each other and eventually compute some assignment that should be globally optimal or close to. The congest model messages are just capped at order log n bits. Okay, so previously there were two known results for load balancing. So in the unweighted setting, when all clients had the same weights, there was a two approximation that ran in order delta to the 5th rounds for bounded degree graphs. And for non-bounded degree graphs, we knew a log n over log n approximation in polylog n rounds. So in this work, we improved the approximation factor to a constant in polylog n rounds. And there's a standard reduction that takes, basically you can solve weighted load balancing with unweighted load balancing, and it just increases the approximation factor by a log n factor. And interestingly, this is basically the only way we know how to solve weighted load balancing efficiently in these models. And so towards a weighted load balancing algorithm in the congest model, we give a better algorithm. We give one that gives a constant factor approximation in the local model. So I just want to highlight a couple techniques that we use to obtain these results. So a quick definition. So one tau matching is just a subset of edges that matches every client at most once, and every server S at most tau of S. So tau is just specifying the server capacities on a server by server basis. And we make heavy use of this key lemma in this work, which says that if there exists some client perfect one tau matching, that's a one tau matching that matches all the clients, then any 1-2 tau matching that's not client perfect has a short augmenting path. So in particular, a path of only length log n. So if we can compute a 1-2 tau matching without any short augmenting paths, then we get a client perfect matching, which gives us an assignment. Okay, so almost immediately, actually, this lemma implies an unweighted algorithm. The key missing piece is how to actually compute a 1-2 matching without any augmenting paths of length log n, this middle line. That's implied by previous work. But I just wanted, I can't really explain to you why this algorithm works or obtains a constant factor approximation, but I just want to show you that there's a simple algorithm, or simple to state algorithm. And one of the cooler applications, in my opinion, is this distributed rounding that we demonstrate. So suppose I give you some fractional assignment F. So every client is basically sending out 1 unit of flow. And so in this example on the right, the fractional loads are given in red. We would ideally want to round this into an integral assignment. And in the sequential setting, we can do this by using things like cycle canceling. And we know that there are ways to just round this at only losing like a +1 term in the loads. But running these algorithms in distributed setting seems hard. Like cycle canceling, we don't know how to do, or shouldn't be. It's too costly to run in distributed setting. But the fact that there exists a 1 tau matching with these server capacities, which are just +1 of the fractional loads, means that we can use this key lemma to compute a 1-2 tau matching. So we just compute a 1-2 tau matching without short augmenting paths, and that's an assignment whose load vector is pointwise less than 2 tau. So this is one of the key like building blocks in our weighted local algorithm. And yeah, if you're interested in more details on any of this, I encourage you to watch the longer version of the talk. And here's a quick summary of our results. So we use this key lemma on the left, and we obtain the algorithms on the right. And the main open problem is if we can get a constant factor congest algorithm.
Thanks for the presentation, and congratulations for the award. So there is a question from Yannick Maus. Is all of this deterministic?
Oh, thank you. I forgot to mention, no. So our algorithms are randomized, and that's because this black box, so we don't introduce any additional randomness, but this black box that we use to compute a matching without short augmenting paths is a randomized algorithm. So
I have a question. Do you know if the approximation for the congest model in the weighted case can be improved?
Yeah, I think it can be brought down to a constant factor. And basically, the only thing we don't know how to do efficiently is to compute this fractional assignment. So given that kind of building block I showed in the last slide, you can round a fractional assignment efficiently to something where you don't lose it too much. But computing a fractional assignment, we don't know how to do. So I think there's a couple ways that you might explore this, and yeah, I think it should be possible to get a constant factor. So maybe
Jukia Sumele is asking, what was the constant in the approximation ratio?
So for unweighted, if you just want like min-max, I think it can be brought down to like 4. So our algorithms have this guarantee that they work simultaneously for all norms, and in that case, the constant, like in the analysis, the constant blows up a bit. So just for unweighted, I think it's like 24. And then for weighted, it's like 100 or something. So we're just losing lots of factors of 2s.
Thanks for your presentation again. Next talk is message complexity of population protocols. The authors are Telly Hemmer, James Aspens, David Doughty, Masha F. Carey, and Eric Severson. And Eric is going to give the talk.
Hi, I'm Eric Severson, and I'm going to give a brief introduction to the message complexity of population protocols. And as stated, this is joint work with Dave Doughty, Masa Eftekari, Tali Amir, and Jim Aspens. So the original population protocol model describes a population of finite state agents that undergo pairwise interactions. So for this example, we have 2 states L and F, and to define the protocol, we need to define a transition rule. So in this case, 2 L's meet, one of them becomes an F, and the other interactions are null. So here nothing happens, here one becomes an F. And if you want to talk about time in this model, we consider a uniform random scheduler, and the natural notion of time scales with n uniform random interactions. So that's the average number of interactions that one agent has. For this example, you can prove that in a linear amount of time, you'll converge to a configuration with a single L. So this is giving a simple algorithm for leader election. Now, the original model had some key limitations, one of which were lower bounds. So it turns out there's a matching lower bound, and this simple protocol is actually optimal. You can't do better for leader election. It's also limited to computing only the semilinear predicates. More recent work in the population protocols model has relaxed the finite state assumption, and they've shown that with larger state sets, you can get faster leader election, faster majority protocols, and you can define new problems like population size counting that only make sense if your agents have enough memory to store the population size n. Our work introduces a new notion of message complexity for population protocols. The idea is that the original model assumes 2 agents can completely share their states in an interaction. So if we increase the state set, we're also increasing the communication cost. So we define a refined model that distinguishes this communication complexity of interaction from the local state complexity. So now we can define the state of an agent is going to be the product of a message M and an internal state I. And during an interaction, each agent's update is a function of its local state and the message from the other agent. So we can view the original model as having both constant size states and constant size messages, whereas the more recent results have been using super constant messages and super constant states. So our work focuses on the natural intermediate, having still constant size messages, but allowing the state set to grow super constant. So to give a first example of a protocol that we give using constant size messages, we consider the problem of junta election. So for this problem, the goal is to elect a junta of agents. But this has been shown to be the key large state primitive for both efficient leader election and majority protocols. So if we can solve this problem, we can solve the other problems that people care about. And our junta election algorithm works with a level variable, similar to the others, that has a distribution that decays doubly exponentially. And it can be shown that the maximum level that any agent has will be about log n, and the junta will be all the agents that hold the maximum level. So now other protocols can simply broadcast the level to each other, but that would use messages that scale with n. That'd be on the order of log n size messages. So our protocol is going to use only 1-bit messages. And to do this, it's going to rely on timing of internal counters. So every agent locally is going to store their level that they would like to share with each other. They would like to broadcast the max, and they're going to have a local counter. And we're going to use only 2 messages that we're going to call stop and go. So the rule is that the counter is partitioned, where in the green regions, the agents are going to send the go message. In the red region, they send the stop message. And at the end of the red regions are locations we call doors. And the rule of the protocol is if an agent is at a door, if its level is strictly bigger, it can keep counting. But if its level is less than or equal to the door, it has to meet a go agent before it can proceed. So the idea is that the agents with a larger level are able to bring the whole population with them. And once we get to the maximum round, the whole population should be roughly synchronized and they all stop at the final door. And data from simulation confirms this along with our proofs that show that this gives a correct with high probability algorithm that uses polylog time and space. And here we can see that the max, average, and min counts are all very similar, and they all stop at the final door. For another example, we solve the problem of exact size counting. Our exact size counting algorithm uses the leader, and the intuition is the leader would like to distribute 1 unit of mass via synchronized averaging phases. So here we have a population of 7 agents. There's 1 leader with mass 1, the rest have mass 0. And we're going to use a message of 5, we're going to use a message set of 5, and the message can be interpreted as discrete units of weight that partition the interval of possible masses. So we have synchronized rounds using a phase clock, and during the round, the agents average their weights. So here 0 and 4 become 2, 0 and 2 become 1s. And then at the end of the round, it can be shown by existing lemmas that all of the weights are within 3 consecutive values. And once all the weights are within three consecutive values, well, then we can zoom in and redefine the scale of weights. So this means that the interval will shrink every round. So here now we're from 0 to 1/2. By the end of round 4, we're from 1/8 to 3/16. And eventually the interval that all the masses are contained in is so small that there's only 1 fraction 1/n contained in there. And thus all the agents can terminate and they know the exact value. So here n equals 7, and you can prove it takes log squared times. It takes log n of these rounds. Finally, in our work, we give a complete classification of the computational power when we ignore time complexity. And we require now probability 1 computation. So first we have a lower bound showing that if we have constant size messages, but the internal states are sublinear, then we can only compute the semilinear predicates. So this is exactly as weak as the original model. However, once we have a polynomial number of internal states, now we can achieve a slow, space-bounded Turing machine simulation. In addition, if our internal states are allowed to grow unboundedly, we can still get a Turing machine simulation, but now only using 1-bit messages, so only 2 message states, which again is the minimal possible number of messages to do anything in this model. And thank you for your attention, and I encourage you to watch the full video for more details and longer animations. And I would be happy to answer any questions.
Thank you for the presentation. Maybe you can unmute Andrea Rita as a question. You
okay.
Mute and ask.
I was just asking if in the counting algorithm, precision would be an issue there. I'm not sure I understood it fully. So because you keep on, the intervals keep on shortening, but
yeah, so it's very quick. So the agents, the number of local states they have is exactly enough to store n, and that can be shown that they have enough memory that they will have the appropriate intervals, and then once their interval is small enough, they actually are able to terminate, so they don't need to keep using more states.
So the message only sends 0, 1, 2, 3, 4 or something like that, right?
Yeah.
When the states,
In addition, there's some overhead to run the phase clock and run the synchronous rounds, but if we assume that the phase clock works as intended, so like with high probability the phase clock's going to work, and then we can prove everything happens nicely.
Okay.
There's a low probability of error, but then you can add a standard trick where you have a slow backup, and you can actually get this whole algorithm to have probability 1, if you'd like.
Okay. Thanks.
So we have another question. Maybe I don't
Yeah.
see the complete name. Daniel, you could please unmute and ask.
Okay, so I can see the question. It's where does each level get the level from? So in the analysis, we assume for simplicity a randomized model where we can just generate the level locally. However, there's standard techniques in population protocols called synthetic coins. So if we would like to only use determinism and just use the randomness of the scheduler, there's a standard way to use synthetic coin flips and have the agents generate their level as they're going, and that will perform exactly the same.
So I have also a question. Which are the hypotheses about the distribution of the interaction?
The distribution of the interaction?
Yes, or how nodes interact. Each node.
Oh, it's the complete graph.
Infinitely often. I don't know.
So the standard scheduler that's considered is a uniform random interaction of the complete graph. And going back to the original definitions here. So the original population protocols model actually considered an arbitrary communication graph, but basically all the work that's talked about time complexity, for the dynamics they define uniform random interactions that are picked. So that's like this well-mixed assumption that every pair is equally likely to run into each other. And that makes the dynamics and the probability much more tractable, I think is the main reason why all the works have done that. So we assume the same scheduler model that is standard to all the other work. Thanks
again for the presentation.
Great, thank you.
So the next talk is distributed computation with the continual population growth. The authors are Dacheng Cho, Matthias Fugger, Corbin Hopper, Manish Kushwaha, Thomas Nowak, and Quentin Subeiran. And Thomas Nowak is giving the talk.
Okay, thank you. So our paper is about computing in a population where your agents duplicate all the time. The motivation clearly comes from biology. In synthetic biology, you can engineer cells just by introducing foreign DNA into the cells that compute, that process some inputs into outputs. Of course, at some point, if you keep on putting more and more processes into single cells, the cell will be overburdened, and which is why a distributed approach has been explored in the last few years. Of course, here you solve the problem of resource limitation inside of a single cell, but you buy the problem of communicating correctly. In cell-to-cell communication, as is the case for many things in biology, there's a certain noise that is pervasive, that is existent. And we developed a consensus-based approach to deal with this kind of noise. Maybe just very formally, from a mathematical perspective, what we are looking at is chemical reaction networks. That's the formalism that is used usually for populations of cells. And there you have some species and some reactions between those species. Here in the example that we gave, it's the reaction A going to A plus A. What this would do is it would remove one A and would put two A's back. So this is a duplication reaction. Each reaction also has a rate constant. So this defines a continuous time Markov chain. This is the formalism that we're working. The first problem that we looked at is amplification, actually. And for that, we have a very simple protocol, which we call the AB protocol. And we have two species, A and B. As do all our cells, we have a duplication reaction for both of them, and then a single reaction on top of that, which is annihilation. So whenever A and B meet, both A and B are annihilated. And if you look at an execution of that protocol, everything here is a Markov chain, everything is random. So you will see some A's reproducing, B's reproducing, A's and B's meeting, so they will annihilate. And at some point, very often you see that only one of them survives. The main mathematical result that we have about this AB protocol that we use for amplification is the following. So let's denote by N the total initial population, and by delta the total initial difference between counts of A and B. Then the protocol reaches consensus, meaning that only one species is present in expected constant time and in logarithmic time with high probability. Also, if we look at we can also look at the question, which of the two species will win? And there we have the result that if the gap is large enough, so more than order of square root n log n, then the majority will win with high probability, the initial majority. And here just a comment. So here the required delta, the required initial difference is sublinear. So you don't even need 51% of the majority for it to win. We also ran some simulations to get a better feeling for what is going on. Here in the graph, we have on the y-axis, we have the probability of species A winning. And on the x-axis, we have the difference, initial difference between A and B. So at difference 0, right in the middle, we have 50% A, 50% B at the start. And by symmetry, this translates into a 50% chance of A winning. And then if we go to the right from that point, A is in the majority. And if we go to the left from that point, B is in the majority. And what we see here is a quite sharp threshold phenomenon that we have. And what's interesting here is that this is the difference between A and B that seems to play a major role. It's not the ratio, but really the difference. It gets a bit less sharp if we increase the population, but it still stays sharp. Okay, once we have the amplification down, we looked at Boolean gates. Here an example of an AND gate. There's an AND gate of two inputs, A, B, one input, y, one output Y. And the idea is, of course, that we use the Boolean gate and then some amplification, as is done in electrical circuits. For each of the signals, we have actually two species. We use a dual rail encoding. So it means that for every Boolean signal, we have two species, one that represents the value 0, one that represents the value 1. And in terms of analysis of this Boolean gate, in this specific example, an AND gate, we have two difficulties. We have noise at the input and at the output. That means at the input, we expect some non-correct inputs, they duplicate. And we also expect, if there are some non-correct inputs, to have some non-correct outputs. They also duplicate. So kind of we have to show here that the gate produces fast enough of the correct output species, for it to take over the output. So put both things together on one slide. So we have a NAND gate or a Boolean gate in more generality, and we have our amplificator that we want to run afterwards. And with this, in theory, you can build any Boolean circuit that you like. Thank you.
Thank you for the presentation. You have a first question by Yuval Emek. How do you define time in this model?
Oh, this comes from the continuous time Markov chain. So every reaction has a rate attached to it, and the propensity of a reaction is the product of everything involved, of all the counts involved, times its reaction constant.
Okay. Yuval, you can unmute if you want to answer to the answer.
Yeah, okay, no, I think that I get it now. So you assume exponential clocks or something like that?
Yes, everything is exponential here. So everything is every reaction is an exponent. The next time of a reaction is exponentially distributed, and its rate is given by the product of the input counts times the rate constant of the reaction.
Okay, thank you.
And there is another question. Eric, could you unmute and ask, please?
Yeah. So your AB protocol is very similar to the approximate majority population protocol. And also from skimming the paper, though, it seems like you're able to prove its correctness much more concisely. So I just kind of wanted intuition for how your protocol differs from approximate majority, why there's a shorter proof.
Indeed, it's similar. The population protocol also has annihilation and duplication, but what is there is you can never outgrow your initial population. Mm-hmm. And also the rates are also different, but that's a minor point. Why the proof is simpler, I don't have an intuition for that. So it seems that just this point of view that we took of two species that duplicate over time, all the time, concurrently, that apparently that led to a simple proof.
I have a question. When you say expected time O of 1, it somehow seems like there should be a setting of this that collapses to the special case of just, say population protocols or, equivalently chemical reaction networks with 2 inputs, 2 outputs. So, but there it would take log of n time for, starting with a gap between A and B of about square root of n. So can you give some intuition why in this model you're always getting expected time O of 1 rather than the worst case that applies in the original model?
Right. So what we did here, maybe I should have mentioned it at the beginning, but we assume a constant volume. If we refer to a volume that scales linearly, then we come down to log.
So I think that's the answer to Yuval's. I had the same question as Yuval. We said, how do you define time? Because the typical way you would kind of make time and chemical reaction networks map to population protocols is make the volume approximately equal to the current number of agents.
Makes sense. And in this case, we have logarithmic time.
Okay, gotcha.
Thanks again for the presentation. So next talk is spread of information and disease via random walks in sparse graph. The authors are George Jacupis, Heike Saarbrücken, and Thomas Sauerwald, and Heike is going to give the talk.
My name is Heike, and I will present our joint work with George Jacupis and Thomas Sauerwald, as mentioned. In this work, we study the information dissemination problem and analyze an agent-based protocol where agents perform a random walk in a sparse graph specifically. So let's start by introducing the protocol we study. It's called visit exchange, and initially given a graph, and one vertex of this graph is initially informed, the source, and that's shown in red here. And then n agents are distributed according to the stationary distribution of G, which means that the position of each agent is random but proportional to the degree of each vertex. And then these walks perform a simple random walk synchronously. And then when an agent visits an informed vertex, it becomes informed, again, shown in red here. And then when one of these informed agents visits an uninformed vertex, then that vertex becomes informed. So eventually all these vertices become informed, and the number of rounds until that happens, we call it broadcast time. And here we study the broadcast time for visit exchange, specifically for sparse graphs. So we've studied this process previously in comparison with more standard rumor spreading protocols such as push. So in our previous work, we showed that in non-regular graphs, push and visit exchange protocols are not equivalent in terms of their broadcast time. For examples, you can have a look at that paper. But in that paper, we also showed that for dense regular graphs of sufficient density, the two protocols have the same broadcast time with high probability. This is natural to expect because in visit exchange in these graphs, each vertex contains exactly one agent in expectation at every round. So you can think of this agent pretty much following the push message. So the proof is a bit technical, but that's sort of why that's the intuition. And now we aim to complement this result by considering the sparse case. The sparse case is a bit more challenging because you may have situations where certain part of the graph is empty, so that's hard to make progress, and you have to argue that this happens rarely. The lower bound on the degree that we had previously helped this argument. So now we try to relax it. First, actually, I will show a surprising counterexample where there's a 3 regular graph, but in this case, visit exchange is slower than the push by a logarithmic factor. I won't go into the details now, but you can have a look at the main presentation for it. On the upper bound side, our first result bounds the broadcast time with respect to the average degree of the graph. What's interesting about this bound is that there is no analog of it in push or a related process. For example, this means that visit exchange in trees, which have an average degree of 1, take polylogarithmic times the diameter number of rounds, but that is not the case for push. In the main presentation, I present the proof of this result. The next result we have is for regular graphs, but now they are complementing the earlier results we've had. And in this case, the visit exchange time is d times the diameter plus an additive term. And this additive term, we conjecture that is actually log square n, but it cannot be better than that because of the counterexample actually we had. Our next result is on expander graphs where visit exchange runs in logarithmic time. This is also the case for the rumor spreading protocols, including for larger values of d. In this work, we've only proved for d being constant, and we don't have a tight bound for the remaining of the cases, but believe that it should still hold. And the next 2 results we have are on specific graphs, balanced trees and grids. First of all, on any binary tree, we show that the bound on broadcast time is h log h plus log n, and this is tight for binary trees. This actually means that for binary trees, visit exchange is slower than push. However, as b increases, it becomes faster. At the extreme, we have the star graph, where in which case push is very slow, but visit exchange is logarithmic. The intuition here is that when the graph has hubs, then visit exchange seems to be faster than the rumor spreading protocols such as push. And finally, we prove that in constant dimensional grids, the broadcast time of visit exchange is asymptotically the same as the diameter. And to prove this, we use and simplify a scaling technique developed by Kesten and Sidoravicius. So with this short presentation, I hope I interested you in the moving agent processes. I invite you to have a look at the longer version of the presentation and let me know if you have questions. Thank you.
Thank you. So there is a question.
Yeah, so I guess all these results are still for regular graphs, which I assume very much help being able to prove things. But any idea how the results and dynamics might change if we can relax that assumption and allow non-regular graphs?
So the first one is non-regular, though there is the condition of minimum degree being at least the same as like asymptotically, that the average degree. We don't know how to circumvent actually this result. Also the binary tree, in that case, the result, the 4th theorem I have, that also holds for b being anything actually. So you can take logarithmic, in which case the graph isn't actually regular. But yes, it's harder to prove, it seems, for non-regular graphs. So yeah.
Thanks again for your presentation. The next talk is who started this rumor, quantifying the natural differential privacy of Gaussian protocols. The authors are Aurélien Bellet, Rashid Gerawi, and Adrienne Hendricks. And Adrienne is going to give the talk.
Okay, so hello everyone, I'm Adrienne Hendricks, and today I will talk to you about differential privacy in Gaussian protocols. So the setting we study is rather simple. So we have a source, in this case Alice, who would like to spread a rumor in a graph. And how she does so is she will just communicate with the neighbors. She will choose neighbors uniformly at random in the complete graph and communicate the rumor to them. So once other nodes are informed, they do the same thing, meaning that they wake up at random times and they communicate the rumor to random neighbors. So an execution of the protocol goes like this. First, Alice sends a message to Bob, then Bob sends a message to Charlie, for example, then Alice wakes up again, also sends a message to Charlie, and finally Bob to Diane. At the end, everyone's informed and the protocol stops. So the twist in our case is that we actually have a curious node. So in our case, it's Charlie, who's trying to infer the identity of the source. So Charlie is trying to know who started the protocol. So in our case, it's just one node for the sake of the example, but in general, there are many curious nodes that collude and share information to determine the identity of the source. The question we ask in this setting is whether this protocol is private, and if so, in what sense? So in order to know whether the protocol is private, we need to know what's its outputs. And so Charlie does not have access to all the messages that were sent. He only has access to the messages that were directly sent to him. So he has access to the ordered sequence of messages, which is that first Bob sent him a message, and then Alice sent him a message. So that's what he has. And that's the output of the protocol from the perspective of the curious nodes. From this, we can define a notion of differential privacy that we introduce in our paper. And it goes like this. If you fix two arbitrary nodes, A and B, in the graph, then the probability that the curious nodes receive messages in a given order, so the output sequence that I showed you earlier, should not be too different whether A or B is the source. And that's a very nice definition because it's independent of the attack, which meaning it depends of the way Charlie decides to guess who's the source. It's very robust to cite information. So even if Charlie knows that some nodes cannot have started the rumor, well, it's robust to that. And it's composable, meaning that if you send multiple messages, then you also have guarantees for this scenario. Actually, we don't study exactly this definition, but a relaxation saying that if some events of maximum probability delta can be much more likely if A isn't the source than if B is. So in some sense, you can have like some privacy leak, but if it's not too likely, it's okay. And with this definition, we actually show that the standard push protocol that I showed you earlier is not private. And in what sense? In the sense that this relaxation parameter delta that I told you about needs to be equal to 1 if you want the guarantee to hold for any graph, meaning that the privacy leak actually happens with probability in the limit of large graphs, which is very bad. So you have an algorithm which is very fast, but with no privacy guarantees. At the other end of the spectrum, you can actually show that if nodes only communicate the message once, and then they stop communicating until they receive it again, then you get a delta of order f over n, where n is the size of the graph and f is the number of curious nodes. And we actually show in the paper that this is optimal. So just communicating once and then stopping to emit is optimal, but it's very slow because the rumor just makes a random walk in the complete graph and you only have one active node at a time. And actually, it turns out that you can trade off between these two scenarios. And if you say that after sending a messages, nodes stop to emit with probability S, with probability 1 minus S, then you interpolate between these two scenarios, meaning that you can have both meaningful privacy guarantees with non-trivial delta and a logarithmic spreading time in the size of the graph. So in a sense, parameterized gossip allows for non-trivial guarantee while retaining this logarithmic spreading time. So that's it. I encourage you to read the full paper for more details, and I'd be happy to take any questions now or offline. Thanks.
Thank you for the presentation. You have a question?
I got the impression that these results talk about complete graphs, and I was wondering how the privacy, this differential privacy, can be affected by the structure of the network.
Okay, so yeah, it's for complete graphs, and the thing is that so we talked about this in the paper and specifically in the appendix. If you want to go to non-complete graphs, then you even need to work with new definitions of privacy, because then, for example, if your graph is a line, then if you take two nodes and there's a curious node between them, then the curious node will always be able to tell whether A or B is the source. So you cannot apply the same definition, otherwise you'll get void guarantees for a large class of graphs. And you need to work with randomized guarantees or restrict that you can only distinguish neighbors, but it is a very weak guarantee because it's not very robust state information. So yeah, I think in the case of general graphs, you need to even tailor your privacy definition to the structure of your graph.
So I have a small question too. How the timing model impact on the result? Is it irrelevant, or if we assume a synchronous or an asynchronous system has an impact on the result?
Okay, so the timing model does not impact the results because in a sense, well, the curious nodes, they get an ordered sequence of messages. And if you assume some delay, well, it has as much chance of helping privacy as degrading it. Like, it can delay your first message to make it look like you're not the source whether you are, but it can also work the other way around. So actually it's, so we don't analyze it in the paper rigorously, but we actually tried to analyze it on the side, and it did not impact the result too much. So it changed some epsilon things in the lower bounds, but it wasn't, it has very little impact on the results.
Okay, thanks. So we reach the last talk is a brief announcement. Is on decidability of two-process affine models. And the authors are Peter Kuznetsov and Thibaut Ritter, and Thibaut is going to give the...
Yeah, I'm Thibaut Ritter, and I'm going to present you a joint work with Piotr Kuznetsov on a brief announcement on the decidability of two-process affine models. Our issue is that distributed computing is populated with many models of computation with different powers and expressions. And we want to compare these models. And for this, we propose to use the recent proposal of affine representation of models to compare them. The first topological representation of model was of the weight-free shared memory model by Ereli and Shavit, where processes are associated to vertices along with their view. So each state corresponds to a vertex, and the state of a run of a system is represented by higher dimensional simplices to form a simplicial chromatic subdivision. Iterating this protocol gives a model that is equivalent to the weight-free model for task solvability. That is, the task is solvable if and only if there exists a map from some iteration of this model to the output complex that satisfies the task specification. And it was recently proposed to extend this model to a subset of the chromatic subdivision, and shown that it can grasp many models of computation from T-resilience, K-obstruction freedom, or the class of fair adversary shared memory models. And we propose to use this framework to compare the computational power of models. In general, the task solvability of models is an undecidable question. The weight-free solvability of tasks is undecidable for systems with more than 3 processes. And we want to answer whether a model A is stronger than a model B, in the sense that all tasks solvable in B are solvable in A. For this, we focus on two-process models, and we provide a classification into 5 simple classes that are determined by whether the endpoint of the affine task belong to the task or not, and whether the affine task is connected or not. We show that it is easily computable and that it corresponds to equivalent classes in terms of task solvability, meaning that we can classify all models, all affine models of two processes and provide a complete hierarchy of models in this class. We believe that affine models is a nice characterization of all natural models, and that it can characterize any models of ride runs or shared memory models and hence with distributed objects. And we believe that the relation between these models is decidable in comparison with the undecidability of a task in general due to the nice structure of the task. And a nice starting point would be to look at link connected affine tasks in higher dimensional setting or fair adversaries that are characterized. Thank you for your time, and if you have any questions.
Thank you for the presentation.
I have a question. Here you use path connectedness as the big invariant. Do you have any idea what kind of invariant would be used to characterize higher dimensional affine tasks?
But it would be mostly generalizing to connectivity of higher dimensions between the different carriers. And there is an issue about link connectivity because it is also an important impact on of whether an affine task can solve another one. So the connectivity for the most part for link connected affine task and more elaborate properties for non-link connected affine task.
Okay.
Okay, thanks again. So this was the last talk of the session.